So I'm going to go over some essentials about stability. The transient power angle curve in stability studies, we wanted to always be able to find an equivalent reactance between the internal source of a synchronous generator and the infinite bus when we're talking about the stability study associated with that single machine infinite bus. And then once you find that equivalent impedance or reactance, ignoring the resistance value, then the electric power that is going to be transferred between the internal source and the infinite bus would be associated with equation 1015, E prime V over X equivalent sine of delta. And based on that, assuming that E prime V and X equivalent are all constants and do not change a lot, then this looks like a sinusoid. And PE can be basically in its first half cycle can be plotted versus delta, as you can see in this figure. And in order to find out basically where is the steady state conditions or stable equilibrium point, we would need to intersect the mechanical power associated with the swing equation with PE, with the electric power. And in general, you would find two intersection points. One of those, which is smaller than pi over 2, would be SEP, or stable equilibrium point. And the other one, which is greater than pi over 2, would be the UEP, or unstable equilibrium point. All right, so we did some examples. So for example, here we have a system that is consisting of a synchronous generator, an infinite bus, a line that is connecting basically the synchronous generator with the infinite bus, and an equivalent load represented as its equivalent impedance. In order to study this system, we need to come up with an equivalent impedance between the internal source, which is bus 1, and the infinite bus, which is bus 2. So we can do that through transformation of this y into delta, and then considering that z equivalent in our calculations. And we are going to ignore the resistive part of this z equivalent as well. So this is how the study can be done. And then once we're talking about the small signal analysis, looking at the swing equation, we can see that this equation is nonlinear because of this sine of delta. And in order to linearize this for the purpose of small signal stability, we need to assume that delta would be equal to delta 0 plus delta delta, and everything else in the system would, such as, for example, PM, also would be PM0 plus delta PM, the changes of mechanical power around the equilibrium point value, which is PM0. So once you do that, you can come up with a swing equation, which is shown in equation 1021. And then it talks about the changes over time of delta delta, not delta directly. Okay, delta delta would be the changes around basically delta 0 under steady state conditions. And in this equation, basically we have d and ps and 2h over omega s as constant coefficients. And delta pm is this external basically input to this system. And in order to and also PS is equal to P max cosine of delta 0, which is called the synchronizing power coefficient, which would be the slope of the power angle curve at delta 0 point. All right, so this equation 1021 is in general in this form, in the form of 1023, which has A, B, C as constants, and then D could also be added to the system to represent a differential equation that has external source, and that D would be the same as delta PM first. Now, in order to solve this equation, we need to come up with a characteristic equation, and then based on that characteristic equation, we could have different conditions happening when delta is smaller than 0, where delta is b squared minus 4ac. Then we would have an oscillatory operation or behavior, which is the case for most power systems. And then the response of y would be based on C1, C2 constants, where these C1 and C2 can basically be found based on the initial conditions of the system, or y0 and y prime 0, basically. And when delta is greater than 0, you would have two real, basically, responses in your characteristic equation. And then the solution would be like this, again, based on C1 and C2, where they can be found through these basically statements. And once delta is equal to 0, then C1 and C2 would be found based on these representations in here. Now, we talked about the oscillatory behavior of the linearized swing equation, and that happens when your delta is smaller than 0. And then associated with that, we would have basically the damping and synchronizing power coefficients, which would be both positive, and we have a zeta, which is defined as equation 1024, and that zeta is smaller than 1. And then under these circumstances, basically the response would be of form 1025. So this is the same type of response that you would get basically in here as well. So this is more generally stated, but in the case of your swing equation, this would be the response associated with the delta that you would be receiving. And in here, you have omega n and omega d defined as the natural and the damped frequency of oscillations. And based off of that, delta omega can also be found based on the derivative of delta over time. And delta omega would represent the changes of frequency around its steady state value, which is basically 2 pi 60 for us. And then based on that, we did a solution of the linearized swing equation. And we could see that the response for delta and frequency, F, could be found based on these plots. And this is when there is only a change in initial conditions and there is no external force. But due to the external force, we did another example in here. And all of these solutions have been also uploaded in Canvas under these MATLAB scripts. So in both cases, when the system is stable, you can see that the frequency goes back to 60 hertz under a small signal, basically stability study. And same in here, but yeah, that's a sign that the system would be stable, right? We want the frequency to go back to where it was before. There is some oscillatory, basically, response, and then we have the same frequency as was pre-fault or pre-disturbance. But in terms of delta can vary from basically one steady state value to another steady state value, okay? This was the summary of small signal. Now, let's focus on transient stability and equal area criterion. Let's go back to the same swing equation. So in this swing equation, we had basically, and forget about the damping. So damping, we stated that damping factor, or D, when positive, will always help out with the stability of the system. So the most pessimistic case would be the case that you don't have damping, and then you want to realize whether the system would remain stable after a disturbance or not. And when we're talking about transient stability, we're talking about big changes in the system, like one generator goes out or one transmission line goes out, or there is a fault in a transmission line, these types of changes. So the swing equation here basically has PM and PE on its two sides. PM is the mechanical power and PE is the electric power. Once these two are equal to each other, based on this swing equation, delta would be constant, right? We wouldn't have any changes in the delta value. But once there is a disturbance in the system, then we want to analyze how the system will look like. And we came up with some basically mathematical manipulations, and then based on that, we came to the conclusion that if the system is going to have a chance for stability, then this integral at some point in time needs to become 0. So if you have the integral of delta 0 to delta of PM minus PE d delta, at some point in time, we need to get to a 0 for this. And this delta 0 is the initial angle, or the angle under steady state conditions. And delta would be basically the delta at a certain point in time, delta of t in general. And then we could look at this transient stability from two sides. The first is when you have the mechanical side of the system to change. You have some extra mechanical power coming from the mechanical side, and you want to see how much extra mechanical power you can push into the system without the system becoming unstable. So that's our goal in here. So we saw that based off of this P versus delta curve. So in this P versus delta curve, you have the PE curve, which is represented as this half sinusoid. And then you have the PM0 line, which is representing the mechanical power pre-disturbance or pre-basically change. Now, we're going to go from this PM0 to PM1. We're going to push more mechanical power, which means that if we're going to be stable, then our ultimate power factor angle would need to go from delta 0 to delta 1, where delta 1 is the intersection point between PM1 and your sinusoid, or point B. So we have to settle down at point B at some time. But prior to getting basically to this point B, if they are going to be stable, we will have some oscillations of angle between delta 0 going all the way through delta 1 and then pushing through delta 2 and then coming back and then oscillating technically between around basically delta 1, between delta 0 and delta 2. But since all systems have damping, we would be having some oscillations which would basically damp out. And then you have these oscillations becoming smaller, smaller, smaller until you get settled at delta 1. So that's the story of becoming stable. Now, in order for that to happen, basically, we have two areas that we can focus on. And these two areas would be associated with A1 and A2. A1 is the area that is representing how much extra energy we're giving out to our system because of that extra push in the mechanical power. And while we are under A1 curve, we can see that always PM, or the mechanical power, is going to be greater than PE, or the mechanical power. Therefore, under area 1, the system will always accelerate, or we would have basically acceleration in the delta or the power angle. But since we're giving this extra energy to the system represented by this A1 area, we need to give it back. That extra energy needs to be taken back in order for the system to have a chance of stability. And that would be when your delta angle goes beyond delta 1. Therefore, under A2 curve, you can see that always now the electric power is becoming greater than the mechanical power, which means that you would be receiving that extra energy that you gave to your electric system now back from the electric system. Now, if these two areas, A1 and A2, are equal, or we can get to this type of condition, we would have a chance of stability. Now, you can push this PM1 further and further and further and try to see if you can find an area 2 which would be equal to the associated area 1. And the ultimate case is when basically your area 2 would be between basically these 2 points of B and C, where the C point is the unstable equilibrium point of your system under that arbitrary PC value that we're going to look for. Okay, that PC would be that P critical, the critical PC that we can push into the system under the mechanical side such that the system would still remain stable. A little bit just beyond that PC, the system will become unstable. And we came up with the solution through to finding basically that delta C, that would be the associated critical delta or critical power angle, and delta max would be basically pi minus delta C. So we would find that delta max through an iterative solution like this, which would be found from the previous delta max. And then once you find delta max, you can find your delta C also through the relationship between delta max and delta C. And here is the relationship between delta max and delta C. So there was an example here, which you have a system like this. Under steady state conditions, you have a 60 hertz round rotor synchronous generator, which is delivering 0.6 per unit of active power to the infinite bus. The machine has an inertia constant of H equal to 5 seconds. Equivalent reactance between the internal source and the infinite bus is 0.65 per unit, and the excitation voltage and the infinite bus voltage values are at 1.35 and 1 per unit respectively. We want to basically find the steady state power angle, delta 0, and if an extra 0.1 per unit power is pushed through the generator, we want to calculate the new power angle delta 1, assuming that the system will remain stable. And I have also simulated the system using the ODE function of MATLAB, which is a function that solves differential equations for the purpose of simulations. So shows the changes of the system over time. And the plot has been shown in here using that ODE function that has been basically shown in this example 10.4 script. So these are the changes of delta, as you can see. and the changes of frequency, as you can see. So as long as these basically oscillations are sustained and do not become bigger over time, we will assume that the system remains stable. Pay attention that we have no damping in here. Because there is no damping, those oscillations won't decay over time. But as long as those oscillations do not become bigger over time, we would assume that the system remains stable if you're using simulations. Now, if you add a damping factor equal to 2, you will see that these oscillations will decay to 0 over time. Now, there is a trial and error also. There is a trial and error basically approach also to this problem, where you can basically return the damping factor to be 0, and then you would just increase the extra mechanical power until you see the system becomes unstable. And then you can see that the delta PM, or the extra power push, would be 1.837 per unit. So this is example 10.4. So these are the E, V, PM0, dPM, the delta PM. So you can see that under these conditions where delta PM is equal to 0.1 per unit, your system will remain stable. And I think the next example is example 10.5, where we're adding a damping factor into the swing equation. And we initially put it equal to 0, which means that there is no damping in the system. And then we're going to push more extra power. And that extra power is right at 1.80838. Under these circumstances, you will see that the system becomes unstable, which means that your delta and F values get unbounded. Okay. Now, if you just make this delta PM a little bit smaller and run the simulation again, you will see that you still get bounded, basically, results, even though the damping is 0. But since you have bounded, basically, results, then this means that the system can remain stable. But really, this is the borderline, right? If you put 8, then there is nothing you can do. The system becomes unstable, okay? And then once you add damping, so damping always helps out with the stability. Once you add damping, even though that extra power has been pushed, you will still get a system that will be stable. But we wanted to see if you can find a method that, without using the simulation, could help you with understanding what is the basically maximum power that you can push through the mechanical side so that the system can still remain stable. And that's based off those equal area criterion equations that we wrote. So this gives you the example 10.6. Now, in example 10.6, the same system has been now solved in order to find out that delta max. So this is your example 10.6. In this example 10.6, we've been using the same basically while error in the Newton-Raphson method based on this equation 1044 to solve for delta max. And as you can see, the delta max in degree has been found at 125. Delta C, the critical clearing angle, which is smaller than 90 degrees, is 54. PC, the critical mechanical power, is equal to 1.6837. And the delta PM, the critical delta PM with respect to the initial PM0, is once you basically subtract this PC from PM0, and that becomes 1.0837 per unit of power, mechanical power. Okay, now let's go to the electrical side of the system. Changes that happen on the electrical side are even more important. So usually you do not push power on the mechanical side that much. You cannot even do that physically because the system has an inertia on the mechanical side. So even though you want to increase the mechanical power all of a sudden to a big value from what was there, but because of the inertia on the mechanical side of the system, it takes some time so that you really can get to that point. So what we discussed as the extra mechanical power push is not really very feasible physically in basically real time, that delta PM cannot suddenly change. That PM cannot suddenly change from that small value to a very big value. But on the electric side of the system, things are basically different. Electrical systems are faster by their dynamics, by their nature. So things can happen very fast. And this is basically even more critical when we want to see what changes on the electrical side can happen and whether those changes can result in instability or not. So this is what we're going to focus now. And we're going to focus on short circuits, okay, which is faults resulted by faults in the system. So remember, we always talked about when we were talking about a single machine infinite bus, we were looking at one source associated with the internal the excitation voltage. Then we were talking about the infinite bus, and in between there was an equivalent reactance. Now that equivalent reactance and that basically equivalent power that could flow, electric power that could flow from the internal source towards the infinite bus can be viewed at three different periods of time. Pre-fault, when the system is at rest, we are under steady state conditions. That equivalent reactance, we call it X1, and that basically curve of P1 is associated with that time. The curve that you saw under, basically, you can see under pre-fault conditions. Now, once the system goes under fault, we would have a different equivalent, basically, reactance existing between that internal source and the infinite bus. And we call that X2. So generally speaking, that X2 would be a much higher value than X1. See, X1 is X in general is representing the impedance that is existing. The smaller that impedance is, the better your system can transfer power, okay? So we always like that reactance or impedance in general to be smaller in power systems. Under ideal conditions, those impedances would be zero, right? There's no impedance in the system. There's no impedance in the transmission system, for example. But that's not the case in reality. So there's always an equivalent reactance existing between your generator and the infinite bus. So when your system goes under fault, that impedance becomes bigger. That equivalent impedance that is seen between your generator and the infinite bus becomes bigger. And that shows that the capability of your system to transfer power from the generator to the infinite bus has diminished. So we cannot transfer power the way that we used to pre-fault when the system goes under fault. So in general, that X2 would be much, much bigger than X1. Under the extreme case, that X2 becomes infinite. If the equivalent impedance existing between your system and the infinite bus is infinite, then it shows that you cannot transfer any power from your generator to the infinite bus. So if that equivalent reactance existing between this internal source and the infinite bus is infinite, it means that you cannot transfer any more power from that basically internal source to your generator. So you cannot remain under fault conditions always. If you remain under the during fault equivalent reactance and power, then you will certainly lose stability. Therefore, at some point in time, you would need to clear the fault. Now, once you clear the fault, then you would have a post-fault scenario, post-fault situation, where now the equivalent reactance between your internal source and the infinite bus becomes another value, which is not as small as, in general, not as small as X1, but not as big as X2. You come to some kind of compromise. So X1 is small, X2 is very big, X3 in general would be big, but not as big as X2, okay? Which gives you a chance for the system to go back to stability. Now, if the pre-fault system and post-fault system are exactly the same, meaning that the configuration of the system is not changed, it means that the faulted line, for example, the fault that happened on a line in the system was temporary. So you go back to where you were. That type of nature of fault is called temporary fault. Under those circumstances, X1 and X3 would be equal, which means that you go back to the same basically place that you were. But in general, that fault may not be temporary, which means that you need to now take out that line permanently until the crew comes for the maintenance of the line. Okay, keep that in mind. X2 under extreme cases would be infinite. X3 under the best conditions would be a temporary fault, which means that X3 would go back to X1. And if X2 is infinite, then how much would be PE2, the power that you can transfer? Zero, exactly. Because, PE is always equal to some E times some V over X equivalent times sine of delta. That equation, represented by this curve, was some E times some V over X equivalent some sine of delta, right? If X equivalent becomes infinite, P becomes zero. So keep that in mind. All right, so let's go back to where we were before. We're talking about a fault. And because of that fault, we have a pre-fault condition, a during fault condition, and a post-fault condition, each represented by their own X and PE curves. As an example, let's go to this figure 1011. Under pre-fault conditions, what would be the equivalent reactance? That's XD prime associated with this generator plus XT, the reactance of your transformer, plus XL over 2. If you're assuming that these two lines have the same reactance and they're in parallel, then the total, basically X1, would be based on this equation 1044. And what would be your P max 1, the maximum power that you can transfer? That would be E prime times V over X1, right? That would be the maximum power that can be transferred, the maximum point on your sinusoid. Now, if the fault is happening at point A, and this fault is a bolted fault, so impedance 0, that point A is exactly on the bus, right? So if that fault happens, would we be able to transfer any power to the infinite bus? So the current is flowing basically this way. Under normal circumstances, it will flow through the two lines and then power goes to infinite. But if the fault is happening right at bus 1 or close to bus 1 at this point A, will there be any transfer of power? No. Assuming that you have a three-phase fault, there is no chance of transfer of power to the infinite bus. So under those circumstances, X2 under scenario A would be infinite, and P max 2 under scenario A would be 0, right? So bus 1 is point A, fault happening at bus 1, or one of the lines near bus 1. So close to bus 1 on this line, for example, this line 2, at this point, okay? So there is no distance really. This is a circuit breaker. So here also at point B, if the fault is happening on one of the lines close to basically bus 1, under that basically scenario, also X2B would be 0 and P max would be 0, okay? But if the fault happens at point C, which is the middle point in one of the lines, in line 2, for example, can you say the same thing, that there would be no basically power reaching the infinite bus anymore? Can you say that? No, you really need to investigate that, because there would be a path of power through line 1, right? So you need to investigate that. And in order to investigate that, the best way is to construct a single line diagram of the system. So look at your infinite bus. You look at your internal source. Look at all of those components that are existing in the system. And point C was the middle of your line 2, right? Now, that point C is being grounded because of the fault. Therefore, you were always in transient stability studies, we need to always look for a direct impedance that is existing between the internal source and the infinite bus. So therefore, you can again convert that scenario into that Y into a delta and find that X2C. Okay, so once you do that, your X2C, you see that, will be found through this representation, which is not infinite. It's a value, and therefore your P2 max, your P max under this scenario would be E prime V over that X2C. Okay, so that you need to investigate. Now, if the fault that happened at any of these basically points was temporary, once you clear the fault, it means that the configuration of the system goes back to the pre-fault, right? Under those circumstances, then X3 would be the same as X1. But if the fault is not temporary and is a permanent fault, if the fault is permanent, then you would see the X3 to be equal to X prime D plus XT plus XL, because this line 2 has gone out, right? So keep that in mind. So this gives you that. In general, X1 would be smaller than X3, would be smaller than X2, right? And this means that Pmax2 would be smaller than Pmax3, would be smaller than Pmax1. Now, this is showing that scenario. So you have this biggest peak is associated with pre-fault, PE1, before fault. This smallest peak is associated with the during fault, or PE2. And that PE3, which is not as high as PE1, not as low as PE2, would be associated with the after fault or post-fault conditions. If the fault is temporary, then this means that PE1 and PE3 would be overlapping, okay? If PE2 is 0, this would be basically the curve associated with PE2, which is going to happen when X2 is infinite. When X2 is infinite, then PE2 would be falling on this line. It won't be a curve anymore, okay? Now, before getting into basically analytical calculations, let's go to example 10.8, which is a MATLAB simulation for a solid three-phase fault in a single machine infinite bus. So consider the following input for the system of figure 10.11. Where is 10.11? Figure 10.11 is this figure. So we're talking about a system like this. And then let's go to example 10.8. So these are all of those basically circumstances. We're assuming damping is 0. And we're going to assume that X1 is associated with the X prime D plus XT plus the two lines getting in parallel. So this is X1. X2 is infinite, which means that we're assuming the fault is happening close to bus, so that there would be no chance to basically take the power from the infinite bus, from the internal source to the infinite bus, from the generator to the infinite bus. And XT would be equal to X1, which is means that the fault is temporary, okay? Once you simulate the system and look at basically the delta and the frequency, you will see that depending on when you clear the fault, the time when the fault is cleared. So look at here. You have a condition where this is happening when the fault is cleared at 0.2 something. So somewhere around this time, we're going to clear the fault. Now we're going to basically change that clearing time through a trial and error and see the behavior of the system, okay? So if, for example, your clearing times is small, 0.10, 0.1 seconds, and a run. Look at here, there is no damping in the system, right? Which means that you get sustained oscillations, but as long as these oscillations are sustained, then we would be good. So if now you make your your clearing time equal to this value, 2605, you see that oscillations are still sustained. But as soon as you go a little bit above that, now you can see that you're getting unstable, right? So we're not really interested in the 0.000 time. That's a very small. As long as, I mean, we are around basically 0.01 of that type of accuracy, we should be good. But the point here is that if you're increasing the clearing time, then you will increase the chances of system to become unstable. Therefore, your protection system will need to act fast. The faster your protection system acts, the better you get a chance of stability. So this was a trial and error through simulation that I just showed you. Now let's go to a more systematic approach. So the more systematic approach is, let's assume that under default conditions, PE2 is 0. All right, so if you look at PE2 equal to 0, then this is what is going to happen. This is PE1 is the curve associated with the pre-fault. PE3 is the curve associated with the post-fault. Now, the same concept, the difference between PM and PE, would be resulting in an area of A1, which is associated with the acceleration. And at delta C, you're going to clear the fault. And the time associated with delta C would be a TC, okay? Then you would go to another curve, which is A2, which is the deceleration curve. Now, as soon as you can, basically, as long as you can find out A1 to be equal to A2, acceleration area is the same as the deceleration area, you get a chance to stabilize the system. So area A1 is representing the excess mechanical energy calculated as the area between PM and PE2. PM and PE2. Look, PE2 is really this line, right? It's not a curve anymore because PE2 is 0. From delta 0 to delta C. And then area A2 is representing the energy dissipated during deceleration, calculated as the area between PE3 and PM from delta C to delta max. And point A is the pre-fault stable equilibrium point. Point B is the post-fault unstable equilibrium point. So consider the areas associated with these 2 points. Point A is a pre-fault stable. Point B is the post-fault unstable. When you equalize these 2 areas, then you will see that the critical clearing time can be found through this equation 1056. And also the critical clearing angle would be this delta C, 1052, and TC. So you can basically solve for the critical clearing angle and critical clearing time through an analytical solution. Using the analytical solution, find the critical clearing angle and time in the previous example. So the same example that we did through trial and error. Now, in example 10.9, we're going to do an analytical solution for that. And delta C, the critical clearing angle, would be found at 1.4796 radians, and the critical clearing time would be 0.26, which is close, right? Almost the same, 0.26. We did this a little bit more into details because we just wanted to find out what is that really, really epsilon basically value that you add to time, and that results in the instability. But that 0.26 is just good enough out of this calculation. Now, under the case that PE2 is not 0, which means that something like this scenario, when the fault happened at point C, the PE2 value was not 0. Under these circumstances, we can find basically the critical clearing angle, delta C, through, again, equalizing these 2 areas, but the critical clearing time cannot be found, okay? So that still needs your simulations. And that critical clearing angle would be found based off of this equation 1059. Again, we have to equalize these 2 areas. Area 1, this A is the pre-fault stable equilibrium point. Point B is the post-fault unstable equilibrium point. Now, in example 10.10 is when the fault is happening at point C, middle of line 2. After the fault is cleared, line 2 would be permanently isolated, which means that in general, the pre-fault, post-fault, and during fault values are not equal. X1, 0.65, X2 becomes high, 1.8, X3 becomes not as high as X2, but greater than X1. Under these circumstances, we cannot solve for TC, but we can solve for basically the critical clearing angle analytically, and that would be 98.834. Now, using trial and error, we can find the critical clearing time to be around 0.4127 seconds.